This is about 60 pounds of bismuth metal. Bismuth is right next to lead on the periodic table, and like lead, it makes a fantastic material for radiation shielding. Now, assuming that I haven't changed the title of this video 18 million times before I actually post this video, you might assume that this is what I'll be using to catch an exploding cosmic ray. But in fact, cosmic rays will actually go right through this. Even though the walls of this container are about an inch thick, cosmic rays don't care, they go right through. So instead, I'm actually going to be using this to remove anything that isn't a cosmic ray, but I'm getting ahead of myself. While cosmic rays may sound like something out of a Marvel movie, they're actually very real, and they rain down on Earth literally all the time. This bismuth canister is actually part of a larger apparatus, which I'm calling my quantum baseball mitt. 1 second, let me get it. This setup is capable of a lot of things. Testing special relativity, catching the aforementioned exploding cosmic ray, and a few other tricks, all of which I'm excited to show you. However, before I can show you how all of this works, I first need to explain what a cosmic ray is, why they're exploding in the upper atmosphere, and how they get all the way down to Earth's surface. And by the end of the video, we're going to see how they not only slow down time, prove Einstein right, but are also used to find smuggled drugs and uranium, and are even used to find secret passages in Egyptian tombs. A lot of the stuff that I'm going to be covering today does build at least a little bit on previous videos. For example, these two detectors were built and used in a previous video. So for those interested, I've put links to those below. Also, all the topics that I'm covering today are inherently huge, so I put a ton of resources down below of extra reading and great videos on the same topics. But keep in mind, I am going to have to glaze over a lot of stuff because these topics are huge. So if you want to learn more, be sure to check out those links.
Before we get to cosmic rays themselves, let's start simple with what's called the standard model of particle physics. It's a collection of particles and the forces that govern their interactions. Think of it like a chessboard. The particles are the pieces, and the forces are how they're allowed to move and interact. And while it definitely has some holes in it, it's the best model of how the universe works that we currently have. But while it may look like there's a lot of pieces, really the only ones that we usually interact with are just these three: electrons, up quarks, and down quarks. These three make up the atoms of basically everything, and the rest are highly unstable or force carriers. The rest generally only occur in the most extreme environments in the universe, like inside a particle accelerator or a star blowing up, or the cosmic rays we're going to get to shortly. At the core of every atom are a collection of protons and neutrons, and buzzing around them are electrons. But you'll notice that there's no protons or neutrons on this graphic of the standard model. For decades, we thought both protons and neutrons were elemental and couldn't be broken down further. But then we made bigger and bigger particle accelerators and found out that if you smash them into something hard enough, they do in fact break apart into smaller pieces. Quarks are those pieces, specifically these two. The up and down quarks are the only two that we actually find in atoms, and they always come in triplets. 2 up and a down make a proton, while 2 down and an up form a neutron. While it's possible to get pairs of quarks or larger combinations like quartets and quintuplets, you'll never actually find a quark on its own. Also, anything other than these two triplets are unstable and will decay very quickly down to either stable triplets or other stable elementary particles. But we'll talk more about that later. The rest of the quarks we can mostly ignore as they're extremely unstable and only exist for fractions of a nanosecond if they are created. Those are all the particles that we're used to interacting with. Now let's look at some of the weirder ones. In the standard model, right next to the electron, we have the star of today's show, the muon. Muons are very similar to electrons and are in the same group. They have the same charge and behave in basically the same way, but have higher mass and are unstable. After they're formed, and we'll talk about how that happens in a second, they exist only for a very brief moment before shedding their extra energy and reverting back into electrons. But while they exist, they are an amazing particle that alone can give a huge amount of insight into the workings of the universe. When I say that they behave like electrons, I mean that they can do basically the same job: orbit atoms, form molecules, etc. For example, if you combine a proton and a muon, you get what's called muonic hydrogen. It has a lot of the same properties, but the resulting atom is actually much smaller. Muon's higher mass lets it orbit closer to the proton, shrinking the apparent size of muonic hydrogen. Atoms, after all, are mostly empty space, so there's plenty of room to squish things down when the muons orbit closer than normal. This has the fun property that it actually makes room temperature fusion possible. This is one of the many reasons why muons are more fun than their less exciting electron cousins. For a brief moment, they make what seems like science fiction possible. Fusion is what happens when two atoms get close enough to stick to each other. Normally, atoms repel each other, but there's this sort of tipping point where they suddenly switch from repulsion to attraction, not unlike having that fifth beer. But normally, it requires heating gas to hundreds of millions of degrees to give the individual atoms enough energy to overcome that barrier. Muonic hydrogen lets the atoms get much closer, and so the smallest nudge is sufficient to get the protons to stick together and turn into helium. Unfortunately, muon's lifespan is about 2.2 microseconds, so they don't last long enough for this to be useful in producing a real fusion reactor and keeping the reaction going. And it takes far more energy to make muons than you would actually get out of that reaction. But still, real room temperature fusion is a pretty neat trick. Speaking of which, how do we even make muons in the first place? It's not like there's a quantum craft store that would let us just paper mache extra mass onto an electron. Well, if you're okay with giving up your dreams of a practical muon-based fusion reactor, we essentially have to do nothing, and 10,000 of the buggers will pass right through you every second. This brings us all the way back to cosmic rays. Cosmic rays aren't actually a specific thing per se. It's an umbrella term for particles and radiation that comes from space. You see, while space is vast, it's also full of a host of big, scary beasties that can produce some of the most ridiculous forms of radiation. Take our sun, for example. The sun is made primarily of hydrogen, but it's so hot and energetic that some of that hydrogen is regularly spewed out at incredible speeds. It takes massive particle accelerators to make protons of the equivalent energy here on Earth, while the sun does it without effort. But the sun is a tiny little nothing star in reality, at least compared to the force of, say, an exploding dying star, the collision of neutron stars, or a black hole when it's feeding. In those even more extreme events, particles can be accelerated to very nearly the speed of light and will contain incredible amounts of energy. Imagine, for example, a single atom with the energy of an entire 100-mile-per-hour baseball, which would be enough that you might actually feel that single atom hitting you. To put some numbers to it, the highest energy particle that we can manage here on Earth using our biggest particle accelerator is 14 trillion electron volts, which, not for nothing, is a pretty high number. The record holder for cosmic rays, though, was 300 quintillion electron volts, which is 7 orders of magnitude higher. We couldn't make a particle with that much energy even if we built a particle accelerator the size of our solar system. Though I will say, the higher the energy, the more rare those particles tend to be, to the point that the highest of highs only hit a few times per day or even per year. Most of the stuff that passes through you is in the giga-electron volt or billion electron volt range. Electron volts is just a measure of the energy of a particle. What it actually means doesn't really matter for the sake of this discussion. Suffice to say that a billion of them is a lot. Several hundred quintillion is an amount that there is no metaphor I can give you that will let you wrap your brain around how unbelievably gigantic it is. All these high-energy particles just fly through space for millions or billions of years, never slowing down until they eventually hit something. In our case, that tends to be gas in the upper atmosphere. Let's use the simple example of a single one of these high-energy particles being a single proton, moving nearly the speed of light, and it hits an atom of hydrogen in the upper atmosphere. At the moment of the collision, that region of space erupts into a spray of particles, and this is one of the weirdest bits of physics in my opinion. As we discussed earlier, protons are made up of 3 quarks. Well, all that momentum our high-energy proton is carrying has to go somewhere, so when it collides with another proton, both are ripped apart into a spray of quarks. However, I mentioned near the beginning that quarks are never found on their own. The reason for this is that the amount of energy needed to pull 2 quarks apart is the same amount of energy needed to spontaneously form 2 more quarks from basically nothing. This way they always remain at least in pairs. This is the part where it should 100% wriggle your brain. After the first 6 quarks are scattered, each will generate a partner quark out of nothing. But there's still too much energy, and so it can rip those new pairs apart, which generates more quarks, and so on and so forth. This process is called hadronization and is something I have never been able to fully wrap my head around. The more energy in the initial collision, the more exotic of quarks can be produced, as like muons and electrons, the other quarks are basically just heavier versions of the usual kind. And more energy means heavier particles can be produced. This is a perfect example of the ability of matter and energy to sort of interconvert. The incredible kinetic energy of the initial particle is traded to generate particles with mass through this hadronization process. Another thing that can happen is what's called pair production due to the emission of extremely high energy gamma rays from this process, which is another instance of the universe being extremely weird. Basically, light is converted to pairs of particles. If you'd like to learn more about that, I've got a whole video about it which I've linked to below. Sometimes, if the energy is high enough, you'll actually get strange quarks generated as the partners to some of the scattered initial quarks. Also, the new quarks that are generated are likely to be some mix of matter and antimatter, and so all kinds of annihilation events can happen. The whole thing is, frankly, a mess. As such, I can't cover every potential particle and decay, so I'm going to glaze over a lot of it. This whole mess, though, is called an air shower, as literally thousands or even millions of particles can come raining down, a lot of which is generated sheerly through the conversion of kinetic energy into matter, as well as all of that junk colliding with atoms in the atmosphere that gets propelled downwards or blown apart when some of the other pieces hit them. Since most of the quarks end up as pairs rather than triplets, they are very unstable. But we still give them names based on what quarks they're made of, as each pair can have radically different properties. For example, if the pairs are made up of up and down quarks, we call these pions. But if things get a little strange, and a strange quark ends up in the mix, they're called kaons. There are more, but even just pions and kaons come in 3 or 4 flavors each, and so I'm not going to get into them. Generally, if kaons are going to form, it happens within the first few collisions, as there just isn't enough energy to generate strange quarks further down the progression. They almost immediately decay, though, as strange quarks are super unstable, and depending on the charge of the kaon, you can get some mix of pions, or occasionally muons and neutrinos. Another reason you get thousands of particles by the time the mess hits the ground is that one positive kaon can decay into 3 pions, which means you're now essentially getting 5 new quarks from the energy of that one decaying strange quark, all of which can go on to split again and make even more pions, or crash into things on the way down and blow more atoms apart. Once you hit pions, the number of ways that things can decay dwindle, and so the majority of what you get out are muons and gamma rays. Muons and electrons being the main byproduct of pion decay. Compared to the other particles in the air shower, muons are fairly long-lived. Muons decay over 2.2 microseconds, while the rest will have decayed within fractions of a nanosecond or less. As such, essentially none of the rest of the particle zoo makes it to Earth's surface, and so all we generally detect down here are the muons and some gamma rays. Everything else either decays or is absorbed by the atmosphere. So one of the easiest ways to look for these explosions of particles is to see if we detect any muons coming down. When a muon's approximately 2.2 microseconds is up, they decay in one of 2 ways depending on if it's a matter or antimatter muon. Matter muons will convert to electrons and release the extra mass energy as pairs of neutrinos, while antimatter muons convert to positrons, which are the antimatter equivalent of electrons, and again shed 2 neutrinos. Just quickly, one of the reasons that we know about all these different particles is because of the advances of particle accelerators. When we crash particles together, we're essentially recreating these explosions. If you've ever wondered why there are all these trails in images from the LHC and other colliders, it's because of processes like hadronization generating new particles from the input pair of protons that smash together.
Alright, that's enough particle physics for you to understand muons and where they come from. The first thing I want to do today is actually detect some of them. Doing so is basically catching some of the debris from the cosmic ray explosion that happened above me. And after I've done that, I want to not only catch a muon, but I want to catch it decaying back into an electron within my detector. From there, we can actually use this setup to measure some of the properties of the muons themselves and see why they prove Einstein correct, and why they're useful for catching smugglers or exploring Egyptian tombs. Which means it's finally time to talk about the quantum baseball mitt. The secret sauce to this whole setup are the 2 detectors, one in here and one in here. Each of these detectors contains a special material called a scintillator. This one uses a plastic scintillator called BC412, occasionally shortened to bicron, whereas that one uses a gigantic hunk of sodium iodide. Scintillators are really neat in that when radiation goes through them, it induces tiny flashes of light by interacting with the crystal's structure. The higher the energy of the radiation passing through, the brighter that flash of light. Now, I'm making it sound like the flashes of light are a lot brighter than they really are. In reality, it's maybe a handful of photons, and so very few, if any, cameras can really see that.
So instead of a camera, I've stuck the crystal to a special kind of vacuum tube called a photomultiplier tube. This takes those few photons from the flash of light and converts it to a very large electrical pulse, which is much more easily detected. Both of these detectors are homemade, and I showed that process in a previous video. Each detector is connected to a special piece of hardware called a gamma spectacular, which takes those electrical pulses and converts them to an audio signal, which can be interpreted by my computer. By analyzing the size of the pulses, we can actually make a spectrum of energy of the things passing through the detector. Low energy things make small pulses, and high energy things make bigger pulses. And when graphed, we can see the energy of the radiation that surrounds us.
But this alone won't show us which of the flashes are the muons and which are just high energy background radiation. Well, now, we could just assume that anything on the very far end of the graph that's extremely high energy is the muons. And later we will do that. But first, I want to prove that those flashes are indeed muons. To be able to do that, we need to know what direction they're coming from. If we can see that they're coming down from space and they're high energy, then it's safe to assume that they're actually muons. And this is why I have two detectors. By having them spaced a couple of feet apart, I'm able to do what's called coincidence detection and get directional information. The way this works is that I'm looking for pulses that come from both detectors simultaneously. Muons are moving at essentially the speed of light, so when one comes down from space, both detectors will register the event at essentially the same time. Even though there's a minuscule time delay, it's so fast that my hardware can't actually tell the difference, and so both pulses come through at the same time. They're set up this way so that the plastic, less sensitive one acts as a trigger and is up top, and then the lower, more sensitive one is able to give me a spectrum of the event. This way, I can look at all of the coincidence events that I register, and all of the muons should be bunched up on the far high end of the graph. However, the problem with this is the setup doesn't care which of the two directions the particle is actually coming from. If it comes up through the ground, it's just as likely to set off the detector. There's a variety of naturally occurring radioactive elements that can emit very high energy gamma rays which could confuse the system and look like a muon. Alternatively, if regular background radiation comes in through the sides, it could hit both detectors at the same time and be registered as a pulse. To prevent all of this and cut down that noise, I've put the lower detector into my bismuth shield. Bismuth, again, like lead, is extremely dense, and so muons are one of the only things that can punch right through it like it is even there. This cuts down on the noise and gives me a much cleaner spectrum.
Speaking of bismuth, this special canister was actually made by the sponsor of today's video, the Bismuth Smith. Normally, he makes these beautiful and expensive bismuth sculptures and crystals that he sells on his site, and the sheer variety of items is really amazing. When we first got talking about potentially partnering up to do a video, he was telling me about how he can make custom pieces out of bismuth and has even developed a process to make them whatever color he wants. So I asked him if he could make me a custom bismuth radiation shield, and he happily obliged. Now, apparently, making this monster was an absolute nightmare because it's a lot of molten, very dense metal to deal with, but he's a professional, so it came out great in the end. Bismuth as a material is actually pretty amazing. It's 8 times rarer than silver, but thanks to the oxide that it forms on its surface, I think it's far more beautiful. And since it's basically as dense as lead, it makes fantastic radiation shielding, but unlike lead, it's not toxic, so it's safe to handle. Which is why I dreamt of having a bismuth-based shield for years. But while this was a custom one-off item, I can't recommend checking out his store enough. The pieces are gorgeous, and there's really something for everyone. I've put some links below for those interested, and if you use the price adjustment code THOUGHT20, you get 20% off your first order. As a fun note, all of those pretty colors come from one of my favorite bits of physics, called thin film interference, which is why he can make them in literally any color or get these amazing rainbow effects. And he's so certain of the quality of the items that he offers a 100% money-back guarantee if you're not ecstatic about your order. Okay, let's put the shield to the test and see if we can detect some muons. Unsurprisingly, it works beautifully, and I started getting muon detections immediately.
Oh, there it is.
When we look at the spectrum after an hour or so of recording, there's a huge spike at the far end of the spectrum, which are all the super high energy muons I'm looking for. The best part about this setup is I can just set a threshold and only count these pulses that are high energy, and ignore the rest of the low energy noise. Now that I know that the setup can detect muons, let's try and catch them decaying down into electrons. Since we know that essentially all this super high energy stuff is just muons, I'm going to only use one detector this time. Rather than getting a spectrum, I'm just going to connect the raw output to an oscilloscope rather than my computer. In the process of converting the pulses to an audio signal, the hardware I'm using actually ends up losing a lot of the pulses. But if I open up the device to expose the internal electronics and probe the raw signal coming directly out of the vacuum tube, I can see all the pulses coming through, I just can't graph them. But for this experiment, that's fine. I've set the scope to only trigger when it detects 2 pulses within a time span of 500 nanoseconds to 2.2 microseconds. In theory, what I should see is a big spike from the muon, and within its decay lifespan, a second, smaller peak, which is the electron it decayed into. When it's all set up, all that's really required is patience. The first time I tried this, it was 4 hours before the detector finally triggered. Even though we're being showered with thousands of muons constantly, the decay happening within the small space of the detector is actually quite rare. But sure enough, when it fired, it was the exact pattern I was expecting. And I managed to capture about a dozen more over the span of a day or two. Always the same, one big spike followed shortly thereafter by a little spike. Unfortunately, my camera was never rolling when this actually happened since the timing is so random. But here's where we run into a little bit of weirdness. Muons on average are generated about 15 kilometers up in the air. With a lifespan of 2.2 microseconds, even moving at light speed, that only lets them travel about 660 meters. So few should be reaching us, and most should have decayed away unless they're produced much closer to us. Yet here we are detecting lots of them. And we know that they're produced about 15 kilometers up thanks to surveys done with high-altitude balloons that measure the count rate as a function of altitude. So what gives? Well, the answer to that is time dilation, which means that Einstein is getting involved. Okay, let's make a few assumptions to make this next bit easier, and the assumptions we're going to make should only affect the result about 1%. First, we're going to assume that the muons are all produced at exactly 15 kilometers up. Then, we're going to assume that we're on a locally flat area of Earth and ignore the curvature. There's only going to be three things that affect the flux of muons that we're detecting. The first is that they decay exponentially. So let's pretend that we had a ball of muons holding still. They won't all decay at exactly 2.2 microseconds. Some will go sooner, some will go later, but the whole mass is decaying exponentially. Over time, the number remaining decreases faster and faster until we hit zero. The next is their lifespan. If we tip the detector over by a set angle, we're now no longer measuring muons that are shooting straight down. We're now detecting muons that were produced a little bit further over, and so by definition, they would have had to travel a little further to reach us. The more we tip the detector over, the longer the muons have to travel to reach us. Due to their short lifespan, the further we tip the detector, we should detect less and less muons, as they'd need to travel too far and would have decayed away before reaching the detector. The last thing is the atmosphere. Same deal, the further we tip, the further the muons have to have traveled, and the more atmosphere they have to interact with, and so the chance of them bumping into something or being stopped increases. All combined, the flux we should detect is very low and decreases as we tip the detector over. Something like only 1 in every 10 to the 10 muons should survive the trip and be detected on Earth. So we should really only detect anything when the rig is pointing basically straight up and down. By the time the system is tipped past 30 degrees, we should detect basically nothing. However, what we instead see is that we're getting far more detections than should be possible. Why is that? Well, the closer to the speed of light you move, the slower time actually passes for you relative to the world around you. So what might have only taken you 2.2 microseconds, to an observer watching you go by, closer to 35 to 40 microseconds actually elapsed. So what might look to you like 660 meters, to an outside observer would look closer to 6,000 meters. The universe is basically compressed down for you. Of course, the exact number depends on precisely how fast you're going. In the case of a muon, the difference between going 99.4% the speed of light and 99.8% the speed of light is a difference of about 6,000 meters traveled versus 10,000 meters traveled in your 2.2 microseconds. The more energy a muon has, the faster it has to be going, and the further it'll travel. So instead of 1 in every 10 to the 10 muons, now between 8 and 25% will actually make it to the surface based on their precise energy. Now let's actually do the measurement and see this for ourselves. I set the detector up to take a reading for 2 hours, and then I average the number of counts for everything above a certain threshold to make sure I'm only measuring muons. Then I move the arm 10 degrees lower using the peg and repeat the measurement. This is repeated until I have a reading at every single angle all the way down to 90 degrees where the arm is horizontal. If you want to try this, I'd suggest a longer read of about 24 hours per measurement to remove any sources of noise like the time of day. I took my measurements at night to remove the sun as a source of noise. Sure enough, when I graph my results, it matches well with the predicted curve if time dilation is real, especially that I'm detecting lots of muons even when the detector is tipped over. So with that simple measurement, we just demonstrated one of the weirdest aspects of Einstein's special relativity with 2 simple radiation detectors. The same experiment can be run using 2 Geiger counters and a Raspberry Pi, and the paper I based the experiment on did it that way. I just have nicer gear, so I used it. Technically, if Einstein had known about muons and had these detectors, he could have run this experiment to prove his theory correct. But now for the best bit. Because the muons are moving so damn fast, it means that they fundamentally have tons of energy, which is also what we see on the energy spectrum. But radiation is a little bit weird. Only radiation of a certain energy will actually tend to hit something. If it's got too little, it'll stop before penetrating, or too much and it goes right through. Let's use the example of simple X-rays before we talk about muons. With X-rays, really low energy X-rays can actually be stopped by a thin bit of glass. This is why in earlier projects that use high voltage and vacuum systems, no radiation is detected outside of the chamber. All the X-rays produced get stopped by the glass. But turn the power up, and now you've got a tube that produces X-rays with enough energy to not only pass through the glass, but also partially through you. To make an X-ray image, we rely on some things like your bones being less transparent to X-rays, and reducing the flux that makes it through that part of you. So on the film, we see a dark spot where the X-rays are stopped. Though X-ray film is inverted, so the areas that are less transparent to X-rays look white on the image. However, turn it up even higher, and most of the X-rays will actually pass entirely through you without ever interacting with you. Muons are the same deal, only they have orders of magnitude more energy. So instead of passing through you, they can pass through entire buildings, steel boats, or several hundred meters of rock without really slowing down. If you stick a bunch of muon detectors underneath something you'd like to image, you can see if there's any areas that are more or less dense where more or less muons are penetrating through. That change won't be huge, but with a sensitive enough detector and a long enough read, you can find areas of anomalous density fairly easily because slightly fewer or slightly more muons are detected passing through that spot. In the case of, say, a big container ship, you could spot if there was any lead or uranium in one of the containers because even though muons mostly punch right through those materials, they are denser and so statistically will be more likely to interact with a muon and absorb or deflect it before it gets to the detector below. So you'll find some areas that have anomalously low muon counts compared to other areas. The same works for detecting drug smuggling. Since water is opaque to the X-rays used in most scanners, trucks going through them at the border that have drugs hidden in cases of water or containers of sauces or soups will actually look opaque in an X-ray image and you won't see the drugs. But muons go right through. So if there is a weirdly dark spot on your image, it means that there must be something hidden amongst the watery items as the drugs are more dense than water and are stopping more muons. If you were Walter White, this technology would probably be making you sweat. Conversely, if you stick a bunch of muon detectors into, say, an Egyptian pyramid, you can spot if there are any hidden chambers above the detectors because there'll be less stuff to potentially interact with a muon, and so the count in that spot will actually be a little bit higher. All of these examples are real things that people are doing. There are now several companies that are working on muon-based scanners for trucks and ships to search for illegal uranium and drug smuggling, and a hidden chamber was actually found in the Great Pyramid of Giza thanks to muon scans. And that still only barely scratches the surface of muons. There's also the potential that they are our clearest clue yet that the standard model is broken, because one of their properties is different than what our model predicts. But this video is far too long already, so I've left a link to a great video on that topic below. And that's not even to mention Cherenkov detectors and radio-based cosmic ray detectors and a lot more, so we may revisit this topic at some point in the future. I know this was a ton of information, so be sure to check out the links I left below. Also, this experiment is one I've wanted to do for years, so it was a lot of fun to finally use all of this hardware that I've slowly been collecting for the past 10 years. Also, huge thanks to the original author of the paper this was based on. I've linked that paper below if you want to learn more about the math of how this actually works. Before I wrap up, I need to say a special thanks to my patrons, channel members, and supporters on Ko-fi. You are all amazing and a huge part of why I'm able to keep making videos. And for those interested, supporters get access to my Discord channel, where there's a lot of discussions happening about the various projects I'm working on, and a lot of other fun stuff. So for those interested, or if you want to just help keep the flow of science videos coming, there's some links below. But that's all I've got for this video. If you've enjoyed, you know what to do. Hit that like button, subscribe, and ring the bell to see when I post new videos. And of course, be sure to follow me on my other social media pages to see updates on the projects I'm working on long before they end up in videos. That's all for now, and I'll see you next time.
God damn it,